We've got a few more practice problems to go. Why don't you pause the video here and see if you can figure out how to solve these two problems. As soon as I see STP, I write down that standard temperature is 0 degrees Celsius, which is 273 Kelvin. So we're given temperature, and we know standard pressure is 1 atmosphere. So we're given a pressure, and we were given a volume. So I know a volume, a temperature, a pressure, and we want to know grams, which I think, in order to get to grams, I need to know moles. So that's my question mark. That makes me think I'm going to use PV equals nRT because that equation has all of those variables. So I plugged in PV equals nRT, my pressure 1, my volume, which is 5 liters, equals N. There's my R that has the atmosphere label, and my temperature, 273 Kelvin. Let's divide both sides by what is attached to N. So 0.0821 times 273, which means I'm dividing both sides by 22.4133. If I do 5 divided by 22.4133, I get an N value of 0.2231 moles of chlorine. We want grams. So let's go from moles to grams. I added up 2 chlorines to get a molar mass of 70.9 grams of chlorine for 1 mole of chlorine. Moles and moles will cancel off, leaving grams. My calculator says 15.816, but I want to finish with 3 significant figures since the only number is 5.00, which is 3. So I'm going to stop right there at 15.8 grams of chlorine. For part B, we are trying to find the volume in liters. So I do not know my volume of 42.4 grams of oxygen. So I look at that and go, got to get to moles. So I did this first step here. I went from grams to moles. 1.325 moles of oxygen is equal to 42.4 grams of oxygen. At STP, so I'm given temperature and pressure. Temperature is 273 Kelvin, and standard pressure is 1 atm. So our only unknown variable here using our ideal gas law is V. And to get V by itself, we're going to divide by 1. So this whole thing divided by 1 will just be my volume. My calculator spit out 29.6976. This would be liters. Let's look at significant figures. We started with 3 significant figures with my mass. So let's finish with 3. 1, 2, 3. That 9 will make that 6A7. So 29.7 liters of oxygen gas. Here's another couple problems. Why don't you pause the video here to see what you can figure out. Let's look at this first part. Chlorine gas is used to purify water. How many moles, it's asking us to find N, of chlorine gas are in a 7-liter tank, that's our volume. If the gas has a pressure of 865 millimeters of mercury, that's our P, and a temperature of 24 degrees Celsius, I added 273 to get it right to Kelvin, so that's our T. We're given temperature, pressure, volume, and we want to find N, so we're going to use the ideal gas law equation. So I put in my pressure, my volume is equal to N. I use the R that had millimeters of mercury, so the 62.4, and the T. I did 62.4 times 297, so I could divide both sides by that 18,532.8, and that gave me an N value of 0.3267, and I want 3 sig figs. So I'm just going to go 1, 2, 3. That 7 will round that 6 to a 7. So 0.327 moles of chlorine. Let's look at part B. We are told that isobutane gas C4H10 is used as a propellant in aerosol cans of whipping cream, shaving cream, and suntan spray. What is the pressure? So we need to find P in atmospheres. We are told that we have 0.125 moles, so we know our N, that's going to go there, of isobutane in an aerosol can at 21 degrees Celsius, so I converted that to Kelvin, that's our temperature, and has a volume of 465 milliliters. I put milliliters right into liters, so I moved the decimal back 3 spots, 0.465 liters, because my R value, my constant, is in liters, atmospheres, moles, Kelvin, so that needs to be in liters. So I multiplied 0.125 times 0.0821 times 294, and I divided both sides by my volume to get P by itself. And therefore, it gave me 6.4885. I'm going to look back, and I should have 3 significant figures. So 1, 2, 3, 8 will round that up to a 9, 6.49 atmospheres. Why don't you try this problem, and we'll check answers in a minute. When I read through this, I saw that butane is used as a fuel for camping stoves. We have 108 milliliters, so that's a volume, but I'm going to put that into liters before we get any further. 0.108 liters. And it's at 715 millimeters of mercury and 25 degrees Celsius. Let's add 273 to get that into Kelvin. What is the mass in grams of butane? Well, in order to find mass, we got to get to moles first. So we're going to find moles, and then we can go moles to grams, because I can find the molar mass of C4H10. Not a problem. Let's use our PV equals nRT and solve for N. So N, we're going to take our pressure times volume, so our 715 times the 0.108, and divide it by R times T. We're going to use the R that has millimeters of mercury. All right, that will give us how many moles of butane. And then I'm going to take that moles of butane and go from moles to grams. I added up 4 carbons and 10 H's to get 0.241 grams of butane. Pause here to figure out A and B. Here we go. It says, what is the volume in liters? So we need to find V. We're told that we have 1.2 grams of carbon monoxide. Before we even get any further, I'm going to put grams into moles. 1.2 grams of carbon monoxide. I went grams to moles. I added up 1 oxygen and 1 carbon to get 28 grams. So I found out how many moles, which is my N, of carbon monoxide. We're told that it's at 8 degrees Celsius, so I added 273 to figure out our temperature in Kelvin. And we're told it has a pressure of 724 millimeters of mercury. That's our P. I'm going to plug all of this into our ideal gas law equation here. So I'm given P, we need to find V. We know N, R, and T. So I simplified the right side of the equation and divided it by 724 to get V by itself. And I got V was 1.0379 liters, and I want 3 significant figures. So I'm going to stop after that 3, and that 7 will round that 3 up to a 4 to get 1.04 liters. Part B says, what is the pressure? So we need to find P. I'm going to circle P here. We're told that we have 1.23 grams of methane. I'm immediately going to go from grams to moles of methane, so we know our N, our moles. We're told a volume, 3.22 liter container, and we're told that it's at 37 degrees Celsius, which is 310 Kelvin. So the only thing we don't know is our pressure. So I set it up into our ideal gas law equation and divide both sides by 3.22 to get P by itself. I used the R constant that had atmospheres in it because that's what we want our pressure to be in. We should get 0.6078, and with 3 sig figs, that 8 should round that 7 up to an 8, so 0.608 atmospheres. Pause a minute here to try to solve for these 2 problems. This problem says, what is the molar mass in grams per mole of an unknown gas? We're told that it's in a 1.5 liter container. That's a volume unit. We have 0.488 grams of the gas. Now in the past couple problems I've gone grams to moles finding the molar mass, but I don't know the molar mass this time, so I'm going to hold on to this mass for a minute. We're told that it's at a pressure of 0.0750 atmospheres, so that's our P, and we're given a temperature. I converted it to Kelvin. So we know P, V, and T. If we know P, V, and T, we always know R, we can find moles. And if I can find moles, I can then do grams divided by moles to get the molar mass. So let's plug and chug. Here I put my pressure, and my volume is equal to my N times R times T. I divided both sides by whatever 292 times 0.0821 was, which is 23.9732. That gets rid of that. And when I do my left side divided by 23.9732, I get an N value. It's very small, 0.004 469,274 moles. But we're not done yet. We want the molar mass, which is in grams per mole. So I'm going to take the grams that I was given in my problem and divide it by my moles. And I got 103.99, but with 3 sig figs, I would stop there. The 9 is going to make that 3 of 4, 104 grams per mole for the molar mass. This problem, again, wants molar mass in grams per mole. So let's solve for moles, and then we can take the grams that we're told in our problem and divide it by the moles. So we're going to solve for N. Let's look to see how you did. PV equals nRT. Again, we needed to solve for N. So I plugged in the pressure and the volume. Notice that the pressure was in millimeters of mercury, so I used the R that has millimeters of mercury in there. I multiplied these two together and got a large number, 18,595.2. So we divide both sides by that. And we would get a small n again, 0.00145,788 moles. Then I took the grams given to me in the problem, divided by the moles, and I got 146.1 grams per mole, 3 sig figs, so we can just cross off that last one and get 146 grams per mole. Why don't you pause this here and see if you can solve for A and B. Let's look to see where you started. We are told that if we have 12.8 grams of aluminum reacting with HCl, we want to know how many liters of H2 would be formed. So I want to know volume that's formed, and we're given pressure and we're given temperature. So if I use ideal gas law to find out liters of hydrogen, PV equals nRT, if I need to find volume, I have to know pressure, which I'm given. I have to know temperature, which I'm given. I can use the R value that has millimeters of mercury, but I have to know moles of hydrogen. In order to find moles of hydrogen, I'm given grams of aluminum. I can get to moles of aluminum, and then I can look at my mole ratio of aluminum to hydrogen. And there's 2 moles of aluminum for every 3 moles of hydrogen. That'll give me moles of hydrogen to plug in for that N value. This gives me moles of hydrogen. Again, I went from grams of aluminum to moles of aluminum using molar mass. And then I looked at my mole ratios, looking at aluminum to hydrogen, the ratio, and I gotta have my moles of aluminum on the bottom to cancel out moles of aluminum that's on top. And I got 0.7166 moles of hydrogen. That's our N value. Now we can plug in our pressure, our moles, our R, and our T to solve for V. If you do all of that, we should get a volume of 18.13 liters, but with 3 sig figs, we'll leave that just at 18.1 liters of hydrogen. In this problem, we're given volume of hydrogen, we're given the temperature, and we're given the pressure. It wants to know how many grams of aluminum will react. Well, given pressure, volume, and temperature of hydrogen, I can plug that in. If I know pressure, volume, temperature, we always know R. We can find moles of hydrogen. Then I can go from moles of hydrogen to moles of aluminum, and then moles to grams using the molar mass of aluminum. Let's plug it in. I solved for N, which is moles of hydrogen gas, given pressure of hydrogen gas, the volume of hydrogen gas, the temperature of the hydrogen gas, and the R constant that has atmospheres in it, since that was our pressure value. Now that I have moles of hydrogen gas, I can look at my balanced equation and say, well, for 3 moles of hydrogen gas, there's 2 moles of aluminum that's used. And then I can go one step further because those will cancel out. And then I can say, well, 1 mole of aluminum has a molar mass of 26.98 grams of aluminum. And I got 8.214 grams. Again, we want 3 significant figures, so 8.21 grams of aluminum. 8.21 grams of aluminum, or 8.22, I guess, if I did a little calculator error. Here are 2 problems looking at partial pressures of gas in a mixture. See if you can solve A and B, and we'll go over them in a minute. The first thing I noticed was that it said an anesthetic consists of a mixture of cyclopropane gas and oxygen gas. So we have 2 gases in this mixture. The mixture has a total pressure of 1.09 atmospheres. The partial pressure of the cyclopropane is 73 millimeters of mercury. So these are in different units. We need them to be in the same unit. what is the partial pressure in millimeters of mercury of the oxygen? So let's get our total 1.09 atmospheres into millimeters of mercury. We know that there's 760 millimeters of mercury in 1 atmosphere. So that gives me a total pressure of 828.4 millimeters of mercury. And we know that partial pressure is the pressure of each gas added together to give us that total. And we're given the cyclopropane, so we just need to take our total and subtract the cyclopropane to get our partial pressure of oxygen, which should be 755 millimeters of mercury with 3 significant figures. This one says another anesthetic contains nitrous oxide gas and oxygen gas. So those are the two in our mixture. The mixture has a total pressure of 786 millimeters of mercury, so that's my total. And we know that the total is equal to each gas added to one another. The partial pressure of the nitrous oxide is 0.110 atms. I took the 0.110 atms and converted it into millimeters of mercury because it says what is the partial pressure in millimeters of mercury of the oxygen. So I took my total and I knew my pressure of the nitrous oxide after I changed it to millimeters of mercury. So in order to get my partial pressure of oxygen, I need to subtract 83.6 from both sides. And that would give me a partial pressure of my oxygen of 702.4, but with 3 sig figs, we would leave it at 702 millimeters of mercury.